I am still seriously blue shifted.
That's because you don't
Thing back on. So I know a couple of you I have for lab. If you log back into the lab segment of Canvas, I went through and manually turned all of the submissions over to digital option for acceptance. The only thing this seems to have caused problem-wise is even for assignments that I already graded, that were just, given to me as paper, sometimes it will give you this weird red oval beside the number that says missing, which obviously is not missing. I don't know how to solve that problem. We may just kind of have to live with it. Canvas definitely is sort of problematic in some of its options. So if it claims you're missing more stuff than you're actually missing, just don't be surprised. If it has a number there, it means you already turned it in and I graded it. I don't know why it's doing this weird coding thing. It's like, it seems to me that like if there was a number there should be some, okay, again, I suck at programming, but it seems like there should be like a default thing where if there's already a number entered, it doesn't show it as missing. But yeah, like I said, I don't know how to fix that. So if you notice that, I am aware of the problem. I put a little blurb about it at the top of the Canvas section for lab, because yeah, I don't know how to fix that part. So the biggest thing I want to do tonight is go through the homework set, which I had glitched a little bit in that I put a due date on for it, but I didn't hit save last Thursday. So I didn't realize that I hadn't hit save on it until about halfway through the weekend, and so I just activated it then. So if you turned in homework on Saturday or Sunday, that was fine. I was aware that I hadn't like turned it on so that it would remind everybody that they were supposed to attach their files. So let me pull up homework then. All right, so this is all the quantum homework stuff. And the first couple of questions really focus pretty heavily. Oh, and I realized I don't have a lambda on the bottom of my, this, like I said, this is what happens in part when I convert from handwritten answer keys to digital ones. I forgot to put my lambda on the bottom of my E photon equation there. There's my lambda. All right. So C equals lambda nu is the major starting point as far as equations go. Your speed of light, C, is in meters per second. But I gave you information in megahertz. And hertz, we also know, is seconds to the -1, not megaseconds. So you have to insert your exponent in order to turn it to just hertz by itself as a unit. Otherwise, you end up with the wrong exponent after you've divided. So 106.9 times 10 to the 6th is 106.9 megahertz. I did my little algebraic rearrange, and you should get 2.8 meters, which is fairly typical for a radio wave. When we looked at segments of the EM spectrum on kind of the overview chart, radio waves are down pretty far toward the long wavelength end of the spectrum. So it makes sense that it's about not quite 3 meters. Calculating the energy for a single photon. So not a very large amount of energy for just one photon. If you did it for a mole of photons, you would probably end up with a positive exponent. But when you are doing it for a negative or for a single photon, you end up with a fairly dramatic negative exponent. So going through this equation here, H is your Planck's constant, tiny, tiny number, 6.626 times 10 to the negative 34th. Speed of light pops up again, 3 times 10 to the 8th. I didn't actually convert my wavelength to true scientific notation. All I did was make sure that it was in meters as opposed to nanometers. So I just left it as 310 out in front. 310 times 10 to the negative 9th. It worked better from a sort of calculating point of view, unless you put another set of parentheses along the top. It kind of works a little bit better to do the top, write down an answer, and then do your final division to give you 6.41 times 10 to the negative 19th. I noticed a few people, I think, were not paying attention to the positive negative sign for the exponents, and some people gave me answers that had the right number there, but they gave me 10 to the positive 19th. It's got to be 10 to the negative 19th for just one photon. Calculating frequency. So back to the idea that frequency is seconds to the -1. I gave you a wavelength. This time I gave it to you actually in meters, 1.2 to the negative 7th. You're back to the equation of C equals lambda nu. Plug in your speed of light, plug in your given wavelength, do your rearrange so that you are dividing. And this one does not have a negative exponent. Hertz or wavelength for a relatively short wave are going to be a large exponent, 10 to the 15th there. Please note that the instructions there for number 4 says write the full electronic configuration. This was supposed to indicate to you that you should not use noble gas notation. As I said kind of in notes and also in lecture last week, I am not particularly fond of noble gas notation. It has a lot of potential errors to it, so I tend to focus on the full configuration options here. So when you look up strontium, one of the things that you see, and actually I realize I need to lean over and grab my periodic table because I don't remember what number strontium is off the top of my head. 38. So 38 electrons have to be placed. Oops, I'm glitching my webcam a little bit there. So 38 electrons have to be placed. And so you always start at the beginning. So 1s2, that's your first layer, 2s2, 2p6, that's 10 electrons. 3s2, 3p6, that's your next 8. You have to follow the Aufbau. Even though that there are some websites that loosely indicate that you don't care what order you write the electronic configuration is, that's actually not true. You do have to obey the Aufbau. Your 4s2 must come before your 3d10. Otherwise, it is not following the correct order of filling. 4p6 and your last final 2 electrons go in the 5s2. So that one was a moderately large atom. Helium, on the other hand, is awfully small. It only has one layer. We've got one s2 and that's it. For zinc, this one has a few less than strontium. For zinc, zinc is number 30, so it has 8 fewer than strontium. It has nothing past the 3d10. So same numbers, they're all maxed out. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and your last 10 electrons in the 3D section. And then bromine is actually on the same row as zinc. It's just a little further toward the right-hand side, and bromine is 35. So it ends with 4p5. Then I gave you a handful of ones that have errors in them. I actually confess to really loving this particular problem. I stole it from a colleague of mine, guy named Matt Seniak, who teaches the Saturday section of Chem 111. He had run across this from a text that he used a while back, and I thought it was a really great idea because it makes you think about what you could have done wrong. So in that first one there, the problem is as written, it has 4d10 after 4s2, when in fact it should actually be 3d10. So that's the major error there. For letter B, they put too big a number above an s. You cannot have a 3 above an s orbital. You can have a 1 or a 2, but you can't put more than that. You can't put 3. Then I love this one especially because it does the thing that I often see as an error, which is one of the reasons why I'm not super fond of the noble gas notation, is it picked up in the wrong spot. Argon is actually number 18 on the periodic table, which is on the 3rd row. So once you have filled up the argon, instead of starting with 5s2, it should actually start with 4s2 and 3d10, and then whatever else comes after that. And letter D has a skip. There are the 2s portion was not shown at all, and it put the 3d10 in the wrong spot. Okay, 3p, then 4s. So I really like the way that it kind of makes you think about, well, if I had made a mistake, what that mistake might have been. Valence electrons. Remember, this is outside layer only. Magnesium, alkaline earth metal column. So 2 electrons. Carbon, 4. Bromine's a halogen, 7. And then we hop back all the way over to the left-hand column of the table, which is the alkali metals. And cesium is just 1. Then I hit you with a couple of just sort of, are you aware how this works kind of questions of how many can you put in a D subshell? 10. How many orientations? Basically, how many pictures are available for the F orbitals? There should be 7. Then we start to hit table trends. Now, one of the things we said about atomic size is that lower left-hand corner is biggest, upper right-hand corner is smallest. So each set either follows a row or a column. Therefore, in the first set, Cesium's at the bottom. That makes it bigger. Then we've got boron, gallium, thallium. So thallium's got to be the biggest because it's the bottom of the column. Same thing true with the halogens. Fluorine, chlorine, I skipped bromine, and iodine. Iodine is at the bottom of the halogen column. Okay, different table trend. Ionization energy. Now, ionization energy is highest up near fluorine. It is lowest down near cesium and francium. So of the first set, cesium not only is the biggest, it also has one of the lowest ionization energies. Going across lithium, carbon, fluorine. Lithium is all the way on the left-hand edge of the table. Therefore, it has the lowest ionization energy. And back to halogens again, might be biggest, but it also has the lowest ionization energy because iodine is much closer to the bottom of the periodic table. Some people gave me more than it asked for on number 11. It says valence configuration only, meaning I don't want to see the inside of it. I only want to see the outside layer. Boron, aluminum, gallium, they're all in the same column there. Since aluminum is in the third row, 3 electrons, outside layer, 2 of them are in the S portion, and the third electron is in the P portion. For blocks, this is the one where you kind of look at the periodic table as a whole and decide, which major group are they in terms of what the last chunk of the periodic table is being filled for the electron configurations. So tellurium is a P block. Neodymium, all the way at the bottom of the periodic table, is an F block. Gold is a D block because it's a transition element. We have cesium, left-hand side of the table, it's S block. Molybdenum, transition metal, it's a D block. And bromine's a halogen, so it's a P block. So one more different table trend. Electronegativity. Fluorine is king. Whichever one is closest to fluorine is going to have the highest value. So bromine is closer to fluorine. You could also look at the number values. We briefly looked at some of the numerical values for electronegativity, but you can also do it based upon the idea of just the trend itself. Bromine's going to have a lot higher electronegativity than either of the other ones. And the last one makes you kind of look at the periodic table and maybe even write out the electron configuration to figure this out. Chlorine only has one unpaired electron, because if you wrote out the electronic configuration, since chlorine is in the second row, it would end with 2p5, meaning that there's one blank spot in the dashes for my orbital notation, but that also means that chlorine has one that doesn't have a buddy, okay? If you conform to the general idea of draw all the up arrows first and then draw all the down arrows second, there's a blank one, okay? That fifth electron in the 2p section doesn't have a down to go with the up one that it has. So paying attention to unpaired versus paired, it kind of makes a difference, and makes more of a difference the further we get into here this next chapter. So questions about this quantum homework set? All right. I want to do a little bit more in talking about bonding. And I'm hunting for, I didn't pop open my file earlier, so I have to like find my right spot here. I think this is the last bit we were looking at last Thursday, talking about polar bonding and the fact that even though there is sharing going on, it's not equal sharing. So one of the things that you can use to help contribute to the idea of whether or not you have a ionic bond or you have a polar bond or you have a covalent bond, this goes back to electronegativity, okay? This is also one of the reasons why in finishing up the end of the last chapter, and we were talking about table trends, we sort of declared electron affinity as maybe the least useful table trend, whereas electronegativity is probably the most useful trend. So now we're kind of circling back to it. So look at fluorine there. Like I said, fluorine is king. It is the electron hog. Fluorine has the perfect score of 4.0. It is the best at keeping electrons close to itself. So if we use this idea, okay, no, also keeping in mind that hydrogen doesn't quite follow the rules. Hydrogen has a value of 2.1 instead of much lower like you might expect it to have. The 2.1 is a value that numerically fits between boron and carbon. So there's some general trends here that we can use in terms of looking at the number values. Most textbooks will agree that if the difference in electronegativity between two atoms is small, 0 to 0.3, we're going to declare that a covalent bond, because either no difference or really small difference. The second category has a little bit of iffiness at the upper end, and I've taught from so many different textbooks over the years. This is why it says some texts go up to 1.9, because I know that if you're looking for additional examples, if you're watching YouTube videos or whatever, you may see a little bit of discrepancy. Some sources claim 1.7 is the upper end. Some go up to 1.9. So a little tiny bit of difference there. If your two atoms have some difference in your electronegativity, we're going to call it polar. But if it's greater than 1.7, and I probably should have put the 1.9 in parentheses there, then we're going to say it's ionic. So part of the way to do this is using the concept that you can actually look at the numbers. What if you're trying to ballpark it? What if you're trying to kind of estimate it based upon just looking at the periodic table as a regular periodic table without all the little number values for the electronegativity values? Then it works better if you kind of look at just the where. So here's some generalizations which are really helpful. We've got the idea that if you have one of the atoms, probably going to be the cation, from group 1 or 2, so alkali metal, alkaline earth metal, and you have the opposite anion, or the opposite end of your bond from group 6 or 7, that actually means you're going to have a fairly big difference between your values. And let me scroll back up here and we can kind of look at my color-coded periodic table here. Actually, can you turn on the oven and throw the meatloaf in to 350? Yeah, I'm trying to coordinate dinner. So anyway, look at the periodic table here. Look at all the values then for alkaline metal and alkaline earth metals. So we've got lithium's 1.0, beryllium's 1.6. We've got potassium's about 0.8, strontium's 1.0. So they're all kind of right around 1-ish. Then we look at the other side, especially the column under fluorine. 4.0, 3.0, 2.8, 2.5, 2.1. So if you subtracted, you would see a relatively large difference there between those two values. So I'm going to scroll back down a little bit here. But just simply looking at the periodic table without having the number values available, you can ballpark it. Now, what if we go the opposite end of the spectrum? 2 of the same element. Well, then that means there's 0. There's no difference in their electronegativity. So they got to be covalent. Now, there's some other ones that are a little more middling, especially if they involve hydrogen. Because remember, hydrogen is this one that doesn't quite obey the rules. It's sort of sitting in the middle of the table instead of off to the left-hand side. Things that are almost always sort of considered to be, I'll call them stereotypical polar bonds are oxygen-hydrogen, part of a water molecule, nitrogen-hydrogen, also sulfur-oxygen. All of those have kind of middling values. But if you go back and you look at them again, I'm going to kind of scroll back up here again. If you look at where the S is, okay, on this, and then the O is above it, oh, well, okay, so there's 3.5 and 2.5, but they're also kind of next door to each other. They're not the same, but they're physically close on the table. You can also say the same thing about like the hydrogen value, okay, not where the hydrogen is, but where the hydrogen value falls. Carbon, nitrogen, oxygen, all of those are kind of sort of close-ish to the 2.1 number. So they all sort of follow the same basic premise there. So all of this is kind of based upon the idea that if you look at the periodic table, even if you didn't have the number values available to you, you can kind of estimate it based on location. So a couple more other things that sort of fall here in the beginning part of this chapter and a half that we're covering here at the end of the semester. If we think all the way back to the beginning of the semester, one of the things we said about molecules was it's the smallest thing that retains all the same properties. So think about like a salt molecule, 1 sodium, 1 chlorine. Well, and it behaves like a salt molecule. But on the other hand, if you hack it apart and you had a sodium and a separate chlorine atom, well, then obviously they're not going to behave the same. Bonding is what holds it all together. Some other things that we run across some mention of, and this kind of dovetails a little bit into some of the other ideas covered here later in the chapter, some things that crop up a little bit. Bonds have characteristics. Now, one of the things that is true, and this makes a little bit more sense at the end of the chapter, but we have to kind of introduce the concept. the distance between the atoms. Well, one of the things that that does for us is it gives us a little bit of an idea on the size relationship. So if you bonded a hydrogen, say, to an antimony, Sb. Hydrogen, obviously, the smallest atom. Antimony is kind of a middle-sized atom. It's down there in the P block of the periodic table. There's some electronegativity difference there, so it's probably kind of polar. You could also then make a little bit of a judgment based upon the fact that since hydrogen's tiny, the bond length may not be all that huge because you have one big atom and one awfully small atom. So you can probably place them kind of close to each other. Bond energy kind of circles back to the thermodynamic end of things a little bit, in that it is usually talked about in terms of kilojoules per mole. Most of the time, we don't measure bond energy for a single molecule. Usually we do it for an entire mole worth of them. Now, it sounds really backward, but the way that they tend to be referred to in terms of how you would make that measurement is they don't talk about the breaking of it. They talk about how much it would take to put them back together. Okay. It sort of sounds like, oh, well, you ought to talk about it in terms of the other direction, but since you want to talk about the breaking end of it, the idea is you are returning the electrons that may have been stolen or may have been shared to their original owners. So this all kind of is sort of tangent information that kind of goes along with some other underlying topics there. So since we just finished up electronic configuration, let's kind of return to hydrogen for a moment. We know that hydrogen is the tiniest. It has one lonely little electron, which also means it's unpaired. And if it buddies up to another atom of hydrogen, which also has an unpaired electron, this is part of what contributes to the covalent sharing. If each one had a blank spot, and then you sit them side by side, they can share. And since they are sharing, that means those two electrons are sort of spending half their time with the left-hand one and half their time with the right-hand one. So this heads us toward two rules. And these two rules are a lot of the basis for a huge amount of the rest of this chapter and also the little bit of chapter 8 that we're going to cover too. Let's talk about the rules for a moment. The first one is referred to by most texts as the duet rule. Hydrogen and helium only want 2 electrons in their valence layer. Now think about that for a moment. They're both super crazy tiny. They only have a valence layer. And helium has 2 electrons of its own. So one of the reasons that I put helium in parentheses there is, even though helium obeys the duet rule, you're never going to see helium trying to bond to another atom because it's happy. It has 2 electrons. It doesn't want any more. It's unlikely to give up the 2 it has. So even though it falls under the purview of the rule, it doesn't really apply in a direct way. Hydrogen does. Now note my almost. The octet rule tends to apply kind of mostly to the rest of the table. We're going to say, as a way of dodging it as a unbreakable rule, that almost everything else would like to have 8 electrons. So we're going to look at the numbers here, and this should look familiar because it kind of harks back to the nomenclature chapter. Remember the nomenclature chapter? One of the things we did in the start before we got around to dealing with transition metals was we kind of looked at the first 2 columns and we looked at the last 6 columns, and we kind of just said, let's ignore the transition metals for a moment. And I just realized that my spacing here is ridiculously wrong. That's the way it's supposed to look. There's actually supposed to be that, and the boron is supposed to be over one more. I didn't realize when I did this that my hydrogen was too far over. Actually, now I've really screwed up the spacing. Okay, so hydrogen is the first column, which, if you look at the third, if you look at the, skip a row for a moment, has 1 valence electron. But that also means hydrogen likes to make 1 bond. It is not large enough to make more than 1 bond. Now beryllium, okay, 2 valence electrons, that's a hark from the last chapter, because it loosely follows the duet rule with kind of a blend of the octet rule, the beryllium stuff and the things that are underneath it. Beryllium and its buddies like to make 2 bonds. And there's boron, aluminum, and sometimes gallium. They have 3 valence electrons. They usually like to make 3 bonds. Then we hit kind of the make or break point, because this is why I talked about the whole nomenclature backtrack for a moment. Back when we were talking about cations and anions in nomenclature, we went +1, +2, +3, plus or minus 4, -3, -2, -1, and 0. Well, ditch all the signs, hang on to the numbers. 1, 2, 3, 4, 3, 2, 1, 0. So the nitrogen column, they like to make 3 bonds because they more cheerfully embrace the octet rule. They have 5 valence electrons, and you've kind of crossed the peak of the mountain. It's easier to steal or borrow 3 more electrons from a buddy than to give up the 5 you have. For oxygen, likes to make 2 bonds because it has 6 electrons, and octet rule, it's easier to steal or borrow 2 electrons from a buddy than to give up 6, because you're way past the halfway point on this section. For fluorine, all the halogens, they've all got 7 electrons. Oh yeah, they're gonna borrow or steal from one from somebody else. And then we've got, okay, no, we're totally ignoring helium because helium is part of its own rule here. But neon and all the other noble gases, they've got 8 electrons in their valence layer, and they hate everybody. Okay, you are almost never, okay, almost is hitting up here again, almost never gonna see them as part of a larger molecule. Yeah, there's a couple of exceptions. So, being that I'm missing a whole bunch of people tonight, let me just make a couple of comments here to kind of round this up. All of these rules, and you can, since you obviously have access to the file, you can look ahead if you like. All of these rules are going to contribute toward drawing of Lewis structures. And I did an enormous amount of cutting and pasting images into this particular notes file so that as we go through them next week, that we can look at a whole bunch of different molecules and how the Lewis structures are drawn. And I know I talked about this a little bit last Thursday night. When you get to the test here in a couple of weeks, the final problem on the test, and there's actually there's instructions on that question on the test, and I'm also probably going to put the same instructions at the top of the test, like when you log into Lockdown Browser. The final question has a handful of molecules that you are going to have to draw Lewis structures for, which then means after you draw them, like literally on a sheet of paper, you either need to take a picture and convert it over to PDF or scan it and make it a PDF, and then send me an email of that page so that I can grade the final question, which is a handful of molecules for the test. So, and I'll talk about that more again next week to just kind of remind people that you're going to have to, in addition to taking the test, you're also going to have to send me a small email file or a small file attached to an email so I can grade that final question. This is a big chapter. This is a big chapter in terms of information and pictures and thoughts that kind of go with it. And I will break out my Tinker Toys next week so I can show them to you and give you at least a hint of how these things actually look in 3 dimensions. Questions? So keep on working on finishing up your lab stuff. Remember that there is, for those of you who have me for lab, my final lab of the semester is on the 7th of December, not the 30th of November. I am skipping a week. I can, if people are interested, I can be available to answer questions on Zoom, but I don't want to do that final Zoomed lab until we have gotten through the overwhelming majority of all of this chapter, because it will make more sense if we kind of delay it a little bit. And that still gives you a week to finish the final lab report. But my suggestion is, since lots of people owe me lab work, is after you done all your magnificent eating on Thursday, on Friday, Saturday, Sunday, if you don't have to work, devote a little time to hacking away at your lab reports so that they can be submitted through the Canvas site, so that you don't have a huge one, so that I don't have a huge amount to grade, like an overwhelming amount to grade the final week of the semester, and also so that you don't have to worry about turning in a whole bunch of files right at the very end. It'll kind of benefit us both if you get some of it turned in the next week or so. Questions? I know I have fewer people here tonight than I usually do. Otherwise, have fun. Turkey, chicken, ham, whatever you guys do for Thanksgiving or not. And I will see you on Tuesday.
Thank you. Happy Thanksgiving to you too.
Bye.
Bye.